Welcome back to the next video, everybody. Today we're going to continue finally trying to prove proposition 5 with part 4 in our series of efforts to do that. So let's get to it. What does proposition 5 say? Let's recall. It says let Q be a finite set of primes as in video 12.3. Then the type Q Hackett algebra T sub Q is a free O delta Q module where this module structure is inherited from RQ, so the type Q universal coefficient ring, via the map phi Q from RQ to TQ, that we know is an isomorphism of complete intersection rings already. So let's prove this finally. Suppose we have rho bar with the usual properties from the chapter and a set of primes Q, as in the statement of proposition 5. First, we require a lemma. We'll call it lemma D. It says, suppose that G is a finite group, that chi from G to K bar across is a character of order D, and that rho bar from G to GL2 of K bar is a representation. Assume that for all G that are not in the kernel of chi, that we have the following. Trace of rho bar G squared over determinant of rho bar G is 1 plus chi of G squared over chi of G. Then three things are true. If D is bigger than 3, then rho bar is reducible. If D is 3, then rho bar is reducible as well. And we can be more specific. We can say it has projective image, which is just A4. And if D is 2, then rho bar restricted to the kernel of chi is reducible. Okay, so this is pretty easy to show. First of all, if rho bar G is a scalar, you can easily check, this is a quick little exercise, that chi of G must be 1, which means that chi induces a surjective homomorphism, we'll call it chi prime, from G prime to CD, where G prime is the projective image of rho bar, and CD is just cyclic of order D. Now, if D is 2, then every element in G prime that's not in the kernel of chi prime has order 2. And so now, lemma D really just reduces to Dixon's theorem on groups that we've already proven. I think, was that last chapter? It was either last chapter or this chapter. Okay. You can also see Diamond-Taylor lifting modular model representations for more details and context. Okay, but really this is just Dixon's theorem in disguise. So let's return to the main proof. Let's let sigma and Q be as they were in video 12.6. Now, notice the hypotheses of lemma D are not satisfied if we try to apply it to the case that we're interested in, which is where G is the Galois group of Q and chi is the cyclotomic character. And the reason for this is because rho bar is absolutely irreducible. So by lemma D, there must be a G not in the kernel of epsilon, such that trace of rho bar G squared over determinant of rho bar G is not equal to 1 plus chi of G squared over chi of G. So here's what you do. What we can do is we can choose a prime P large enough in such a way that Frobenius of P corresponds to G, let's say with Chebytarov density. This result then allows me to find an auxiliary prime P with this property, also not dividing, let's say, 6 an empty set L times the product over primes Q and big Q of those primes Q, such that P isn't 1 mod L. And from this, trace of rho bar Frobenius at P squared is not equal to P plus 1 squared. Okay. We're also going to make a quick little technical remark here. We can replace K at any time by a larger field, and we can assume that our residue field, little k, contains the eigenvalues of rho bar Frobenius at P. Okay. So what I'll do is I'll let sigma be Q adjoin this prime P that I just found. Then sigma is a set of primes containing a prime P bigger than 3, satisfying P is not equal to 1 mod L. That's one of the things we did when we chose P. And this set of primes satisfies the needed conditions to invoke proposition TM twist from the previous video. Let's let gamma also be as in video 12.6, which as you recall is gamma not of an empty set intersect gamma 1 of M, where M is P squared times the product of primes Q and big Q. Choose a maximal ideal frac M of TO as in proposition TM twist from last video. Let H denote the L stilo subgroup of Z mod MZ cross and regard TO, hence TM, because they're isomorphic, as OH algebras via the map D to diamond D as discussed last video. Okay? By proposition TM twist, proposition 5, which we're trying to prove in this video, is now equivalent to the following. We'll call it Theorem O bracket H, which just says that T sub M is a free O bracket H module. Okay, so let's prove this. Again, please review video 12.6 for all needed notation. We're going to be using some differential stuff from that video. Consider the T tilde O module L, which is O homomorphisms from omega tilde O to O, and the TO module L, which is O homomorphisms from just omega O to O. Since since x to x prime, the natural map is unramified, we can apply Riemann-Hurwitz, which gives us the following. The dimension of M2 gamma, so the space of weight 2 modular forms corresponding to gamma is on the one hand g plus s minus 1, because that's just the standard formula for this. But on the other hand, by Riemann-Hurwitz, it's cardinality of h times g prime plus s prime minus 1, which of course is the same thing as the cardinality of h times dim m2 gamma prime, where g, respectively g prime, is the genus of x, respectively x prime, and s, respectively s prime, is the number of cusps of those modular curves. It follows from lemma omega 1 and lemma omega dash 2. So this is part 1 of lemma omega, and this is just lemma omega dash 2. So I think those are from video 12.6. That the k dimension of L tilde tensored up to k is cardinality of h times the k dimension, so this is little k now, so the little k dimension of omega tilde sub little k. Okay? On the other hand, by part 2 of those two lemmas, L tilde mod frac A lambda L tilde is isomorphic to k homomorphisms from omega tilde's kind of H invariant sub k to k, and that's isomorphic to k homomorphisms from omega tilde prime k to k, where what is this frac A here? It's the kernel of O bracket H to H, so it's the augmentation ideal. Okay. Now, because of this, we can apply Nakayama's lemma, which says now that L tilde can be regarded as an O bracket H module generated by d equals dim k omega tilde prime sub k elements. But then by the result from the last slide, any surjective homomorphisms from O bracket H to the d to L tilde must be actually an isomorphism. So that's this fact combined with what we discovered on the last slide here. Okay. Now, what this tells you is that L tilde is free over O bracket H, which is a good start. Okay, but then it also tells you that, let's say, L sub frac n, which is O homomorphisms from omega sub frac n to O, is isomorphic to O homomorphisms from omega tilde sub frac n to O. Like all of these, they're all isomorphic. These all have to also be free over O bracket H, for which frac n's for each non-Eisenstein maximal ideal frac n of T tilde sub O. This is by lemma omega and lemma omega dash 2 part 3. Okay, so we're using a bunch of different parts of those lemmas on differentials. Okay, so this isn't quite what we want though. But rho sub frac m, which is isomorphic to rho bar, is given to be absolutely irreducible. That should say since. Okay, so m tilde cannot be Eisenstein by lemma rho sub frac m from video 12.6. Okay, so we can apply this result from the previous slide to that maximal ideal, frac m, to conclude that L sub frac m is free over O bracket H. All right, still not what we want though. Now, for general rings A, S2 gamma A dual is free of rank 1 over TA. You can see chapter 3 for this. You can also consult Diamond, Darman, Taylor, lemma 1.34, for example. So we have that L tensored up to K is free of rank 1 over T sub K. And L localized at M tensored up to K is free of rank 1 over T sub frac M tensored up to K. Now, on the one hand, if L doesn't divide N sub empty set, then by part 4 of lemma omega, L mod frac ML is isomorphic to K homomorphisms from omega sub K bracket frac M to K. This has to be one-dimensional over little k by that lemma. By part 4 of lemma omega dash 2, the same thing is incidentally true if L does divide N sub sigma, and so N sub empty set, excuse me. So whether or not L divides an empty set, L mod ML is one-dimensional over K. Okay. The reason, by the way, that this part of lemma omega dash 2 applies when L divides an empty set is because by our definition of frac M, TL isn't frac M, and you have to check that to actually apply that lemma. All right, well, now you can apply Nakayama's lemma again to get that L sub frac M is free of rank 1 over T sub frac M. Okay, but then if that's true, T sub frac M must be free over O bracket H, but that's exactly what we're trying to prove. All right? So I think we're done with all of the propositions now needed to prove R equals T in the minimal case. We'll put it all together. We'll put the contents of this chapter all together next video and finish proving R equals T in the minimal case, which will completely finish the proof of R equals T in totality, minus some information about the flat deformation functor that we're going to have to study next chapter, which will be a new kind of series within the playlist. So thanks for watching, and I'll see you next video.